Okay, this is the record of our lecture of 1st of December. Continue to study the variabile aleatorie. How was in English? Variabile aleatoria, how we called it?
Random variables.
Perfect. So we are studying random variables. And what was seen that any random variables had his has density that in the continuous case, today I'll try to speak more on the continuous case, and then after this we shall switch from integrals to sums. So this passage is very simple. Of course, for concrete cases, I want somehow to connect in the lecture of today lecture with different random variables connected with musical therapy, because I promised from the beginning of the course to speak about music therapy and not only about how to say classical probability densities connected with experiments with dices. But we have actually introduced several random variables. These random variables of course we again now let us see. I write more bigger, so please to tell me. This is better or still is small?
No, it's okay.
Okay, thank you. Variables. When we have denoted with x one random variable, it was very simple. We always said that we have density, small function p depending on would be also small p of x. So this shall be small x. This shall be the random variable x. X in our belongs to some interval. Let's say AB, or for simplicity, we shall denote this interval with E, and the property that satisfies this probability density associated with X. This is a function that has values between 0 and 1, and then we have the integral over E of Px dx is identical to 1. For example, x can be the random variable. Probability to have the first node in some of the Mozart musical pieces, the first node to be La. This is kind of random variable. Practically what we shall do, we shall take the part of Mozart unit, and we shall count how many times appearing La. Then we shall take the total number of nodes, and we can say approximately probability is this one. Of course, this is discrete variable, but that discrete random variables, they are very closely connected with continuous random variables, and we shall see that when we use some software, we can in some sense model the process, for example, of hearing, the process of listening, and process of seeing picture with continuous densities. And in this case, we can have models that after we have the continuous model can be transferred to the discrete one. and therefore can be connected with the experimental. So this probability density, of course, if we start with Mozart sonata that are particular units that are studied especially with connected musical therapy, we can say musical piece, the sonata, actually is something that is expressed in time. Therefore, we can have, if we take the random variable x, appearance of La, for example, to say that our small x is distributed. This has meaning the time. For the first moment, the second moment, you have different notes, and then you are speaking about in the moment x, what is probability, for example, La. So this is one event. But also this is one random variable in sense that we are speaking about appearance of the note La during this during the sonata. Now, what we did the last time, so-called expected value of our random variable x. How is computed expected value? This is simply connected with the following integral. Integral over e, our function x times p of x dx. And of course, in this case, in the discrete case, we have a sum of xc, pe, and in the continuous case, we have this integral. And typical exercise given kind of density, probability density, to compute exactly the probability density, and then to compute this moment. When I'm speaking about moments, let me call what is the moment. When you have such density, in general, such integral x to the power kappa of px dx. This we can call moment of order kappa. These moments are very important points, especially in mathematical physics, in engineering, in other branches of the science. That's why from time to time I'm speaking about moments. It is clear that this is the first moment of order 1, and this is very important expectation characterizing globally our random variable. So this is not kind of probability to have x to be a given value, but this is something that describes global behavior of density of the random variable. Okay, another thing that it is important to add here is also the meaning of this probability density. For example, when we are asking what is probability, oh, this should be taken a bit. Now you can see better. Okay. What is probability that our random variable has value A? Sorry, I use this A, so I shall put another letter. For example, This is a kind of interpretation. We have our random variable, and we are asking what is the probability that our random variable has exactly value equals C. And we can say that in this case, this is exactly our small p of C. Therefore, the probability density measures probability that the random variable is C. This is completely compatible also with the discrete case, because in the discrete case, what we had here was, let me write to remind you, for the discrete case, here we have sum of Pj. Pj was probability for the even j. Therefore, when we are asking that probability of our discrete variable is, for example, j, this was exactly measured with this number Pj. Another important thing, again, here with blue, I put analog with discrete case. Let us try to see what is probability that our random variable is smaller or equal than C. For example, if we take probability x to be smaller or equal than j, in the discrete case, what we have to take? We have to take not only Pj, but all P kappa that are before Pj. Therefore, we have to take the sum of all kappa smaller than j of P kappa, where P kappa has again the meaning of our probability density in the discrete case. Therefore, what I have to do, if I have here smaller or equal than C, instead of writing the sum, what I have to write? I have to write integral. Therefore, we shall put here for our discrete case integral. Now we said our interval is A. We have from A to C P x dx. So often we shall measure some random variable, saying probability that the random variable is smaller than C is simply you take integral up to C. If we take x bigger than C, instead of integral from A to C, we have to take integral from C to B. As well, also in this case, if we take x bigger or equal than j, we have to take the sum of P kappa with kappa after j. Therefore, P kappa plus 1 up to all P kappa that are after Pj. Okay, this is important thing. And in some sense, this information is more than sufficient for the first moment, expectation. And now we can go further with explaining some properties of this moment. But before going further, let me ask if you have some questions to be repeated. This we shall repeat, of course, with many exercises.
I didn't understand the moment when you were talking about it.
This one.
Yes.
This is simply definition. Kappa is integer number. Kappa can be 1, 2, 3, 4, 5, and so on. when you compute integral of x kappa px dx, we can consider this integral as generalization of this integral. This is more general notion. This is there is nothing here to like theory. This is simply definition. Say moment to understand that this moment means integral of this x to the power kappa px dx. Only definition. Usual physicists, they call this type of integral moments. That's why to have a common language with colleagues from other branches, I introduce this notion.
Thank you.
Okay, you're welcome. Now, let us say something important for the properties of expectation. Of course, one important property of this expectation. The first important property is if you take your random variable x, say this is, for example, we know that the nodes, they are executed, they are connected with waves with some specific frequency. In this sense, we can say that the frequency of the node La is connected, is determined in such a way that when you speak about Do, then Do is a frequency that is kind of frequency of La. Therefore, we can speak about constant multiplied by our random variable and try to compute this expectation. So what is this? When you have your constant C, then of course you have to compute x, small x, times Cp, the x. And of course, in this integral, you can take the constant C in front, and you have a, let us write, integral x, px, x. And this is, of course, constant a of x. Often we shall also function of our random variable. For example, x to the power 2, or some function. If you have, for example, the expectation of some function of your x. For example, g of x can be x squared, or x to the power 3, or x to the power 3 plus x to the power 2. What expectation of function of our random variable? This is simply, you take, in this case, let us write the integral over I, and here we have gx, px, dx. Let us make some example in order to compute expectation of function of our g. Of course, this property, this definition, we can say, of expectation of function g, is more general than the property A, because here we simply take the function c times 6. If c times 6, then my moment has to have here c times 6. If I have generic function g, then of course I have to put in front of my density g of x. Let us make some example in order to compute, to see how this works. Okay. First example. One. Let us take the following function. Function g for any variable s is exactly 1. This is constant function. What we have to do in order to find the expectation of this 1? So, expectation 1, this one, how is computed? Our function is like you take s to the power 0. S to the power 0 is, of course, 1. So if I take here 1, there I am obliged to take instead of 1. So this shall be integral over I of our px dx. And what is this? This is equal to what you expect. What is the result? This should be how do you think? What was the property of the density? You can use chat if you want. What you expect as a result? Yes? Yes, but g was equal to what? Our function g is identically? Yes?
1.
Identical 1. Exactly. This is the result. So expectation of 1 is 1, according to this rule. If you have any function gx, you put here and you compute your integral. And we know that expectation of 1 is 1. Let us take another example. We take our interval e to be 0, infinity. And then for px, we take a random variable with px. So our random variable x has density that is determined by constant a to the power minus e. Do you remember what was the constant? I think this example we already computed. Integral from 0 to infinity of a to the power minus x is identically 1, if I'm not mistaken. Therefore, the constant c is identically 1. And let us compute expectation of x and then expectation of x squared. These are typical exercises we shall do. How to compute practically? This is what? Integral of x px. So, in order to compute our first integral, a of x, what we have to compute? Integral from 0 to infinity of x. What is p? A to the power minus x dx. And this expectation, I think the last time we computed, this was connected to one integration by parts. And let us see, what was this expectation? Do you remember the result? I think we did one integration by parts. Doing one integration by parts, so representing this guy as derivative with sign minus. First integration, we have to take x, a to the power minus 6, compute it in 0 and infinity. This is 0 in both cases. In infinity is 0 due to a to the power minus 6. In 0 is 0 due to this 6. Therefore, this is equal integral from 0 to infinity a to the power minus dx. And this we already know. This is again 1. And you can see that expectation of 1, the function identically 1, is also 1. The expectation of x is also 1. But this does not mean that x is equal to 1. Only the expectations are the same, but the random variables are different. In the first case, we take gx equal identically 1. In the second case, we take gx equal x. Let us compute now the second moment, therefore x squared. To x squared, let me ask you if this calculation is clear. I think we did already this calculation of this proper integral. If you have some questions for expectation. If not, also the next time when we have tomorrow lecture, please to ask me. Let us go now to compute x squared. If I have x squared, that I'm obliged to put a square. Okay. So when I integrate by parts, again, I have to put the derivative here. So I have 2 times x. But this, as you can see, is equal to the previous case, the expectation of x. And this integral only was equal to 1. 2 by 1 gives me the final result, that is 2. So expectation of x squared is 2. We have bigger expectation here because we take x squared, while for x we have this result. Okay, again, to ask you about your questions, observations. Whenever you have function of your random variable, you compute the expectation in this way. Now we can add to our properties important property, for example, expectation of alpha x plus beta times 1. Remember that 1 was the function that is to x gives the value 1. What we can say about expectation? This expectation means that here I have to take alpha x plus beta. But when you take...
Excuse me.
Please.
Why the expectation of x
square?
Yeah, it's 2 and not -2. Like the minus.
This is very, very important question. Because look here, our probability density, we know that this is function between 0 and 1. So this is positive. I put here x squared, and so on. This is positive. When you take integral of positive function, your result obligatory is positive. Let us now check with the integration by parts. I shall explain you, but this is from generic expectation. We can have a result negative. Because again, if g is positive, x squared is always positive. Probability density is positive. When I integrate, always this is positive. But take carefully here. Here I have minus due to the fact. Now I have to integrate by parts. When I move the derivative, I have 1 times minus. But I have another time minus. Minus by minus give me plus. And this means here the sign is plus. Sign is plus, then here this was already computed, this integral before. This was 1. Therefore, the final result is +2, not -2. We checked from 2 different points of view. From generic point of view, that expectation of x squared is always positive. And also in the integration by parts carefully. Is it clear now the sign, or still you have doubts?
No, it's okay. Thank you.
Okay, okay. Now let us try to see. At any moment, please to stop me when you have some doubts or observation, and we can discuss them. Now, we have A of alpha x plus beta 1. We said the expectation of this guy is integral of alpha x plus beta times 1 dx, integral over I. We know that integral of a sum is sum of 2 integrals. Therefore, I can write integral of alpha x. Sorry, this was px. I forgot px dx. Px dx plus beta in of 1 px dx. Let me see if you see. Can you see here, or I move the camera?
No, it's okay.
Okay, thank you. So you see here I put beta in front because we know that in integral constants can be put outside. Also here I can put alpha outside. And if you see this relation, integral over I, we can say that here we have very simple rule. So this is equal alpha times expectation of x plus beta expectation of 1. And this is very simple rule that we call 3, that also can be used in our calculations. Actually, we know that this is even expectation of already computed. This is 1. So if this is 1, we simply can forget about this guy and write in this form the expectation of this linear combination, alpha x plus beta times 1. Okay. I am leaving for you some concrete examples that you can try to compute by yourself, and then to ask me if what is the result. I am following the book that was suggested, but I shall add some examples that are necessary for our practical exercises. Therefore, the first example is the same px, that is a to the power minus x. Interval is 0, infinity. Question is to compute the expectation of x to the power 2 plus 3 times x to the power 3. Again, from generic point of view, since this function for x positive are positive, this function shall be positive. This is always positive, a to the power minus x. Therefore, the result shall be positive. And the question is to compute this type of integrals. Okay. So this is something that I am leaving for preparation of our practical work. Okay. Actually, till the moment, we were dealing with one random variable. We know that in the real life, we have much more random variables. So from now on, we shall try to clarify the case when we have 2 or 3 random variables, and especially shall clarify what does it mean these 2 random variables at the beginning are independent, because this is very important to have some generic results for our random variables. Kind of properties that show that when you take many random variables, practically you can evaluate probability that these random variables, their some mean value has nice properties. This is so-called laws of the big numbers. We shall speak at the end these properties. But now we start with 2 random variables. So we have 2 random variables. What does it mean that we have 2 random variables? Of course, when we speak about 2 random variables, let's say x and y, in order to define these 2 random variables, you have to define corresponding probability density. And we said that if the probability if these random variables, if you take separately, they have their interval I, where is defined the random variable x, and j is the interval where is defined the probability density of our random variable epsilon. Then we have to take so-called Cartesian product. Therefore, we take the rectangle that is determined by interval I and interval j. We did this on I was interval AB, j was CD, so there was a rectangle determined by this Cartesian product. Therefore, this means if we reserve the variable x for our interval epsilon and letter epsilon for our x is reserved for I, epsilon is reserved for j. So we need to have density that is a function that depends on two variables, x and epsilon. Here, x and epsilon, the couple, the point x, epsilon, belongs to our rectangle E times j. And therefore, in general, to have two random variables, probably they can interact between them. We can say, for example, one of these random variables should be appearance of the note La in specific sonata, and the other variable, for example, appearance of some alpha or beta wave in the angiogram of the patient. Since there is interaction between the music and if we have this measurement of waves in the brain are done with encephalographic. And in this measurement, one can measure the wave, and then again, this wave, alpha wave, for example, this means specific part of frequencies. So we can say that even that the alpha waves are activated, probably is connected with appearance of a specific notes in the concrete sonata. And we can connect events and also corresponding random variables and say there is between these two densities, there is generic model that takes into account both random variables, and in this case we are obligatory to define this density as function of two variables, x that belongs to the domain of the first eigenvalue and epsilon that belongs to the domain of the second random variable. Then in the same way as we defined the probability density, in this case, we can say, for example, this probability that the random variable x is equal, for example, we reserve the letters A, B, C, D for these two segments. We can take now, after a while we shall make a small break. The first event is x to be, for example, mu, and epsilon to be new. By definition, this is simply equal to our probability density in the point mu. And interpret this probability density as probability that random variable x has value mu, random variable epsilon has value mu. So we have two random variables. And of course, in this case, when you take any function g, that is a function of x and y. Let's take now small x and small y. How we compute now, given such function, how we compute the expectation of this function g of xy. This is important. So what you do, instead of taking integral only over I and only over j, you take integral over I and another integral over j of your function g x y. Then you take your function that depends on x and y. So we have probability density xy, and then you integrate in dx and dy. Now we shall give an example to see how this is working, but it is important to know that you have two variables and you integrate in x and y, you have in this sense one double integral. What does it mean? This means you take your functions that depends on x and y, and for the moment, as we did for partial derivatives, for the moment you fix y. You consider y fixed. Here. And then you compute your integral of one variable using the tables of integrals. What you get after computing this integral, this is a function that depends on epsilon. After a while, in example, we shall see how it works. So this is function of y. And I simply integrate this function. When I know this function, I integrate with respect to y. Now, after this integration, x disappears, remains only y. We shall see after this in examples. And you integrate in y this function, and you get your expectation. This is simply important in order to go further. We shall need these very, very simple double integrals. But the principle is the following. Epsilon at the beginning fix, take the integral in x, compute your function of epsilon, and then you integrate in epsilon. This is the plan, the general strategy. Now we shall make small break, and after the break we shall start with some example to see compute the expectation of two random variables, and especially what does it mean that two random variables are independent. In this setting, for the moment, we didn't say what is this density for independent random variables. So let us make the break, and after the break, we shall start with your questions. Of course, this part we shall clarify with example. I stop to record. And